This is Physics Lab Report 1, Newton's second law applied to a basketball rolling across a floor. So the objective of this experiment is to use Newton's second law to describe constant motion of a basketball rolling across a floor. Newton's law states that force is equal to mass times acceleration, or you can say that velocity final equals velocity initial plus force over mass times the change in time. In order to accurately measure the position versus time, I took a video of the basketball rolling across the floor and inserted the video into Tracker software. By clicking on the point mass, I was able to measure distance versus time. The system includes the ball and the earth. The length bar shown in the previous Tracker video is set at 1 foot or 0.305 meters to accurately measure the ball as it moves across the floor. There are several forces which act upon the ball as it moves. There's the force of gravity pulling the ball onto the floor, the normal force of the earth acting upward on the ball, frictional force which acts in the negative x direction opposite of the motion of the ball. In order to create an accurate computational model of this system, I did change some of the script from the Python from Lab 1. The first thing I did was set the ball's mass equal to 3.3 kilograms. Then I found the ball's average velocity from the Tracker data and set that equal to 2.69 meters per second. Then I set delta t equal to 0.033 seconds, which was the time increment used for the data in Tracker. Then I said while t is less than 1.867 seconds, which was the last time position was recorded in Tracker, there was no net force, which means the velocity was equal to the velocity without any change, so the vector is equal to 0, 0, 0. The ball position, however, is equal to the initial ball position plus the vector 0.08877, which was found by multiplying 2.69 by 0.033. As you can see in the computational model, the ball moves in a straight line and at a constant velocity. The position is directly correlated to the time. After extracting all the data from Tracker and from the computational model, I was able to make a graph of displacement versus time for both the actual video and the model in Excel to compare the data. As you can see, the model fits the actual results very well. In conclusion, the model shows that the ball travels at a constant average velocity of 2.9 meters per second. In this case, friction was almost negligible, having very little results on the experiment itself, as shown in previous data obtained through Tracker and the computational model. The computational model accurately describes the actual motion that took place. This experiment was successful. If the axes had been changed, the only difference would have been the constant average velocity would have been negative as opposed to positive.